I'm Will Mars, founder and president of Endurica. If you're working with an elastomer that has a durability requirement, then this talk is for you. I'm going to start with a brief overview of our solutions, but mostly I'm going to focus today on a new feature that we've just launched as of October 1st, and that's the ability to simulate aging effects in a fatigue simulation of a rubber part. And just to quickly introduce my company first, Endurica is a simulation company, and we are 100% focused on elastomer durability. Here, this slide is showing some of the applications that we've done over the years. This is our 12th year since we started up, and you can see we've done quite a bit in the automotive sector, transmission mount, bushings, and so on. We do a lot of work with tires. This is a CV boot. Again, another automotive component. We've done work for like electronics, right, where you have rubber that's an insulator, say. Also work in the oil and gas sector. So these are all applications where you have a rubber component that has a durability requirement. So what sets us apart? One big advantage is that we have the tools and workflows ready to go for just about any durability task that you might want to do for a rubber part. Our tools are purpose-built for managing elastomer durability, and this slide is a summary of the different tools that we offer. So Endurica CL is our classic fatigue solver, and it uses critical plane analysis to make high accuracy life predictions. And the claim to fame for Endurica CL is that it is very accurate, especially at dealing with multi-axial loading. So when you have multiple load inputs, Endurica CL is the tool that you're going to want to use. Endurica DT is our incremental fatigue solver, and it allows you to accrue damage across many different load cases. It can account for material properties that evolve with cycles or with time. It can couple to abacus so that you can update your finite element simulation with material properties that evolve. It can calculate residual fatigue life. Right, so that's Endurica DT. Finally, Endurica EIE is our efficient interpolation engine. And if you have a load signal that is maybe so lengthy that you can't simulate it with your FEA, right? If you've got 1 million time steps, 3 channels that maybe you recorded at a test track, maybe you can't run that in a finite element simulation, but you can use EIE to convert the load history into strain history that you can use for fatigue analysis. Right, those are the major tools, and of course this is just a very high-level overview. If you want to see a lot more detail on one of the particular features that these codes offer and the workflows that they support, go ahead and follow this link. There's a feature grid here that will kind of unpack all of the different workflows that we can support with these tools. This is why 6 out of the top 12 global rubber product companies are using Endurica solutions in their applications. So let's unpack the new aging feature in Endurica DT. What you're looking at here, these are master curves that show how 3 of the mechanical properties of an elastomer depend on aging time. So if you were to take a piece of rubber and put it into an aging oven for a certain amount of time at, say, 80 degrees Celsius, then you would see a time-dependent evolution of the material properties. The properties we're looking at here in the upper left, this is the what's called the intrinsic strength or the fatigue limit of the rubber. You can see at first it goes up a little bit and then it comes back down. In the bottom left, we're looking at the critical tearing energy, right, or the strength, the tear strength of the rubber compound. And again, you can see that as time goes on, there's an evolution. Eventually, with enough time, we see a degradation of the critical tearing energy. And then finally, in the upper right, we have the variation of Young's modulus, or the stiffness of the rubber compound with time. And you can see that in this case, as the material ages, it becomes somewhat stiffer. And so in our finite element simulation and in our fatigue analysis, we want to be able to take account of these time-dependent effects. And the new feature in Endurica DT allows you to define material properties that evolve in time. And the syntax that I'm showing here in this box is the syntax that you would use to define that. In this case, we define an activation energy, right? And that defines the rate at which we progress along the master curve for different temperatures. We have a reference temperature at which the master curve is tabulated that we define. And then finally, we also need to define the actual values on the master curve. So the first column here is the elapsed time in hours of an aging. And then the next column over is the fatigue threshold evolution with time, right? Or the intrinsic strength. This column here, let's see, that'd be the third column over. This is the critical energy release rate. And then finally, the last column is the Young's modulus as a function of aging time. So we tabulate these as a function. These can be direct experimental results. And then we're ready to run the simulation. The code calculates where you are on each master curve by using a shift factor that I'm showing here on the left-hand side of the slide. This is what's known as the Arrhenius law, and the shift factor basically tells you for a given temperature what is the relative chemical reaction rate, right? Aging is a chemical reaction, and at different temperatures it progresses at different rates. And so if we're at a temperature that's different than the reference temperature for the master curve, we need to take account of that shift factor, and we can do that with the Arrhenius law. Now, of course, in a simulation, typically the temperature will be varying in time, and we can keep track of the equivalent time on the master curve for each element in the model by integrating this equation here, right? So this is just integrating the Arrhenius law so that we can keep track of the elapsed equivalent time on the master curve. And so this tells us where we should look on the master curve to get the material properties for that particular moment in time as we're running the simulation. As a first check, what we can do is we can, after entering these properties into the simulation, we can tell Endurica to output the fatigue crack growth rate curve as a function of time. And of course, both the bottom end and the top end of the curve are evolving in a time-dependent manner, and we see that in the crack growth rate curve, right? The crack growth rate curve in the unaged state is the black line that's kind of sitting here in the middle, and then as time progresses, we go to the blue, and then the green, and then the yellow. So at first the strength gets a little bit bigger. In this case, that's what we observed in the experiment. But eventually, of course, as you impart enough aging, then the crack growth rate curve begins to shift to the left, and we start to see a weaker material where cracks grow faster, and so you can see that evolution in the time-dependent crack growth rate curve. We can also look at the strain life curve. Now, if we were to run the strain life curve at different cycle rates, if we run it at high cycle rates, we're going to be on the blue or the green curve, right? Those curves are over here. And at high cycle rates, you can get crack growth, but since the cycle rate is high, not much time passes, and so there's not much aging that occurs, and so aging does not affect the results when you're at a high cycle rate. But if you slow things down, say to 80 minutes per cycle or 8 minutes per cycle, that's the red and the orange curve, then you can see that at longer, right, at lower strain levels where you would normally have longer life, we're seeing that the strain life curves begin to degrade as we accumulate both aging of the material properties and cycles that grow cracks in the rubber. So let's, now that we've kind of seen the evolution of material properties, let's actually do a simulation on a part as a demonstration. And what we're going to do is we're going to do a simple tension dumbbell that is under a cyclic load such that the gauge section reaches 15% strain. So on the left-hand side, you're seeing contours of max principal strain. And you can see that the peak strain is in the middle of the gauge section. As we run this experiment, we're going to age the specimen under a temperature gradient. So in the image on the right, you can see that at the top grip, we're holding that at 100 degrees Celsius. The bottom grip, we're going to hold that at 0 degrees Celsius. So there's a temperature gradient across the strip. And of course, as we hold this for longer and longer time periods, the material on the hot end of the specimen is going to age much faster than material on the cold end of the specimen, and that's going to have an effect on our fatigue life predictions. The definition of the material to include the aging effect is shown in this snippet of text here. This is the material definition. You can see I've got a stress strain law that's Neo-Hookean. I've got a crack growth rate law that's Lake-Lindley. And you can see the aging parameters that I've defined here, where I say the aging type is Arrhenius. Right? We give the activation energy, we give the temperature on the master curve, and then we give the master curves in a tabular format. Now for this problem, we're going to go ahead and run the simulation to failure. And if we look at the part at the time of failure, what we find is that there is well, first of all, on the left, we're looking at the distribution of equivalent time, right? Aging time on the master curve. You can see that the top of the specimen ages much more than the bottom because of that temperature gradient. If we look about 1/4 up the way from the specimen and we check the color scale, it corresponds to about 7 days of aging. And then if we look at the stiffness of the part, right, this was a simulation where we coupled with Abacus and we updated the stiffness of the part, you can see that the top of the specimen has indeed become stiffer by about 40%, right? Red is a 40% increase of stiffness. Finally, if we look at the fatigue life distribution in the part, you can see that when we have this aging under a temperature gradient, the degradation of the crack growth properties along with the increase of stiffness near the grip means that we're going to see a grip failure. We're predicting a grip failure here at the edges of the specimen where we were holding it at 100 degrees Celsius. We can compare that to what would happen if we did not age the specimen. And you can see if we don't age the specimen, then as you would expect, we see the failure at the midsection of the part. And of course, the fatigue life is quite a bit longer, almost 800,000 cycles, versus when we have the aging, we get a grip failure at about 16,000 cycles. So when we include the aging effect, we can account for changes in failure mode, and we can account for time-dependent evolution of the material properties. So that is the new capability. Use Endurica DT to simulate the combined effects of temperature-dependent aging on your stiffness properties, your crack growth properties, on the development of cracks under complex loading. Now here, this was simple loading, but the code works just as well for multi-axial variable amplitude loading. And the fact that we can give a tabular input for the master curves means that you can have very high accuracy. If you've got the experimental results that describe the aging effect, you can get that effect into your model and get durability right. I'd also like to mention that we have a webinar series, and if it's called Winning on Durability. And if you'd like to see these, all of the episodes that we've ever had are posted on our website at the link that we're showing there, endurica.com/business-strategies. So you can learn more about what we're doing there. Thank you.